You are sitting in a room that feels stable. The floor beneath you is solid. Your body occupies a precise location. Time moves forward at a steady pace, measured by clocks that agree with one another closely enough that you do not question them. Space appears empty, passive, and inert, a stage on which matter moves, but which does nothing on its own. This assumption feels safe because it aligns with daily experience and with centuries of physical intuition. Yet according to measurements you already accept as real, the space inside your room is not neutral. It has weight, it exerts pressure, it expands. Even in the absence of matter, even in perfect darkness, space itself contributes to the behavior of the universe. This is not a philosophical interpretation or a speculative theory. It is the direct consequence of equations that accurately predict planetary motion, black holes, gravitational waves, and the expansion of the cosmos. The contradiction is simple and deeply uncomfortable. The most successful description of gravity ever written predicts that empty space should tear the universe apart. The same equations that explain why galaxies exist also imply that they should not. This conflict was noticed over a century ago, temporarily erased by hand, and later confirmed by observation. The question is not whether the equation is correct. It is whether removing it was the mistake, or adding it was. The equation that replaced gravity. You are taught that gravity is a force, something objects exert on one another across space. This idea works well for everyday experience, but it quietly fails when precision matters. Einstein replaced it with something more exact. Gravity is the shape of space-time itself. Matter does not pull, it curves. The equations describing this curvature are compact, mathematical, and extraordinarily successful. Yet embedded within them is a term that behaves differently from everything else, one that does not describe matter or motion, but the behavior of space itself. At first, this replacement feels like a refinement rather than a revolution. Instead of invisible forces acting at a distance, you are given geometry. Objects move the way they do because the space and time around them are bent. A planet follows its orbit not because it is being pulled, but because it is following the straightest possible path through a curved structure. This shift resolves inconsistencies in earlier theories and produces predictions that match observation with unprecedented accuracy. You can test these equations against reality. They explain the slow rotation of Mercury's orbit. They predict the bending of light around massive objects, which you can measure during eclipses or with modern telescopes. They allow black holes to exist as stable solutions rather than mathematical curiosities. More recently, they predict ripples in space-time itself, gravitational waves, which are detected exactly where and when the equations say they should be. In every measurable way, the description works. Because of this success, you may assume the equations are complete, that they simply describe how matter and energy behave. But when you examine them closely, you find they do more than that. They describe how space-time behaves even in the absence of matter. This is where intuition begins to fail, because the equations do not require space to be passive or inert. They allow space to have its own dynamics. In Newtonian gravity, empty space does nothing. Remove all matter, and nothing happens. In Einstein's formulation, remove all matter and energy, and space-time still has structure. It can stretch, it can contract, it can curve in ways that are not directly tied to any object. The equations permit this because space-time itself is the subject of the theory, not merely the background. This feature is not added as an afterthought. It is built into the mathematical form of the equations. On one side, you have terms that describe curvature. On the other, terms that describe energy and momentum. The relationship between them is fixed, but the curvature side does not vanish just because the energy side does. Space does not default to neutrality. It remains something with properties capable of evolving on its own. This is where the unfamiliar term appears. It does not describe particles, radiation, or motion. It describes a property of space-time that exists everywhere, equally, regardless of what occupies that space. Its mathematical role is subtle. It changes how space-time responds to itself. Instead of curvature being driven only by matter, space-time gains a tendency that is independent of local contents. At the level of equations, this term is simple. It is proportional to the metric itself, the object that defines distances and durations. That simplicity is deceptive because it scales with space directly. Its influence does not dilute as the universe grows. The more space there is, the more influence the term has. This is not a special assumption. It is a direct result of how the mathematics works. You may be tempted to think of this as an abstract artifact, something that exists only on paper. But the equations are not optional. They are constrained by observation. Once written down, their consequences must be accepted unless contradicted by data. And at this stage, nothing contradicts them. On the contrary, they align with measurement more closely than any alternative description of gravity ever has. The replacement of gravity as a force with gravity as geometry does more than change language. It changes what kinds of questions are meaningful. Instead of asking how strongly objects attract one another, you are forced to ask how space itself behaves. And once that question is allowed, the possibility that space is not neutral, not static, and not passive becomes unavoidable. This is not yet a paradox. It is simply a feature of the framework you already trust. The unsettling part is that nothing in your everyday experience prepares you for it. Space feels empty. It feels inert. The equations say otherwise, quietly and without exaggeration. They say that even before you add matter, even before you add motion, space already has something to say about how the universe must evolve. A term with no physical intuition. At first glance, the equations appear complete without modification. But Einstein realized that they permit solutions where space expands or contracts on its own. This was not an experimental discovery, but a mathematical inevitability. To prevent this behavior, he introduced an additional term that counteracts expansion. It was not derived from observation. It was inserted to preserve a static universe, because a changing universe felt unreasonable. The unease did not come from data. It came from the equations themselves. When you write them down and assume a universe filled evenly with matter, the geometry does not settle into stillness. It evolves. Distances between regions change with time. The equations do not describe a universe that can simply exist unchanged. They describe one that must either grow or collapse. This result emerges before you specify any detailed properties of matter. It does not depend on galaxies, stars, or radiation. It follows directly from the relationship between curvature and energy. Once space-time is allowed to respond dynamically, stasis becomes unstable. A perfectly balanced universe does not remain balanced. The slightest deviation grows with time. For Einstein, this outcome was unacceptable. You are accustomed to thinking of the universe as something that simply is, not something that changes as a whole. In the early 20th century, there was no observational evidence suggesting large-scale evolution. The night sky appeared fixed. The idea that the universe could be expanding or contracting everywhere at once conflicted with intuition and with the limited data available. To remove this behavior, Einstein modified the equations by adding a term that acted uniformly throughout space. Its effect was to counteract the natural tendency toward expansion or collapse. Mathematically, it introduced a repulsive influence that increased with distance, balancing the attractive influence of matter. If tuned precisely, it produced a universe that neither grew nor shrank. This adjustment was not motivated by measurement. There were no observations demanding it. Instead, it was guided by expectation. A static universe felt more reasonable than a dynamic one. The equations were made to reflect that expectation, not because they were incomplete, but because their consequences seemed implausible. The term itself was peculiar. Unlike other components of the equations, it did not correspond to anything tangible. It was not associated with mass, motion, or energy in the usual sense. It did not arise from known physical processes. It was simply a constant multiplying the structure of space-time itself. Its presence was mathematically consistent, but physically opaque. This lack of intuition mattered. Physics advances by connecting mathematical symbols to measurable quantities. Forces correspond to interactions. Fields correspond to effects. This term resisted such interpretation. It did not describe how matter behaves within space. It described how space behaves independently of matter. At the time, this distinction had no empirical grounding. The balance it created was also unstable. If the value of the term was even slightly off, the universe would either expand or collapse. Maintaining stasis required exact tuning, with no mechanism to enforce it. The universe had to be set precisely on a knife edge and remain there indefinitely. The equations allowed this, but they did not explain it. From a modern perspective, this is the first sign of deeper trouble. When a theory requires extreme fine-tuning to preserve a preferred outcome, it suggests that the outcome may not be fundamental. The static universe existed only because it was imposed. It was not a natural consequence of the equations, but a temporary suppression of their implications. Yet at the time, this modification did not appear reckless. It preserved consistency with known observations. It allowed the equations to coexist with prevailing assumptions. The cost was conceptual clarity. A term with no clear physical meaning was introduced to erase a behavior that felt wrong rather than one that was proven wrong. The important point is not whether Einstein was justified. It is that the equations themselves were already signaling something counterintuitive. They were pointing toward a universe that evolves even in the absence of external cause. The added term did not emerge from deeper understanding. It acted as a restraint, preventing the equations from saying what they were otherwise compelled to say. In this sense, the term marks a boundary between expectation and implication. On one side is the universe as it was assumed to be. On the other is the universe as the equations describe it. The tension between the two did not disappear with the modification. It was merely postponed, embedded quietly in the mathematics, waiting for observation to catch up. The desire for a motionless cosmos. You intuitively expect the universe to be stable on large scales. Stars move, planets orbit. But the backdrop feels fixed. Einstein shared this assumption. The idea that the universe could be stretching everywhere at once conflicted with common sense and with the astronomical data available at the time. The added term enforced stillness, not because stillness was measured, but because it was assumed. This assumption was not careless. It was reinforced by everything that could be seen. When you look at the night sky, the stars appear locked in place. Constellations persist over generations. The Milky Way holds its shape. There is motion within the universe, but not of the universe. Nothing in ordinary experience suggests that the distances between all things are changing simultaneously. Early 20th century astronomy offered little reason to doubt this picture. Telescopes revealed stars and nebulae, but their distances were uncertain and their motion subtle. The universe appeared vast, ancient, and static. Time passed, but the large-scale structure seemed immune to it. Against this background, a dynamic universe felt less like a discovery and more like an intrusion. You can understand why this mattered. Physics does not operate in a vacuum of expectation. Theories are built to explain what is observed, but they are also shaped by what feels plausible. A universe that evolves everywhere at once challenges basic intuition about causality and scale. Change usually has a source. Motion usually has a direction. Expansion without a center violates both instincts. For Einstein, the equations were already radical. They replaced force with geometry, matter with curvature. Asking them to also describe a universe that expands or contracts as a whole may have felt excessive. The static universe acted as a stabilizing assumption, anchoring the theory to familiar ground. The added term accomplished this quietly. It did not introduce new entities or interactions. It did not change how matter moved locally. It adjusted the large-scale behavior of space-time so that, when averaged over the universe, nothing changed. Expansion was canceled. Collapse was prevented. The universe remained suspended. This solution preserved a comforting hierarchy. Local dynamics could be complex and violent, but the global structure remained calm. Time passed, events unfolded, but the cosmic stage itself stayed put. The universe existed in time without being shaped by it. What makes this assumption important is not that it was wrong, but that it was untested. It was not derived from measurement. It was inherited from experience. The equations themselves did not demand it. They resisted it. The static universe had to be imposed against the natural tendencies of the mathematics. This creates a subtle inversion. Instead of theory following observation, theory was constrained to protect intuition. The equations were allowed to describe reality only up to the point where their implications felt unreasonable. Beyond that, they were corrected. At the time, this may have seemed like prudence. Physics had already been destabilized by relativity and quantum ideas. Anchoring cosmology to a stable universe limited uncertainty. It allowed focus on local phenomena without confronting unsettling global consequences. But this choice carried a hidden cost. By enforcing stillness, the theory concealed its own most radical prediction. Expansion was not a speculative addition. It was the default behavior. Preventing it required intervention. The static universe was not the natural outcome of the equations, but an exception maintained by balance. This distinction matters because it changes how later discoveries are interpreted. When expansion was eventually observed, it was not that the universe had begun to behave strangely. It was that the equations were finally allowed to do what they had always implied. The motionless cosmos was revealed as an assumption, not a fact. The desire for stillness also shaped how evidence was evaluated. Without clear measurements of cosmic distances and motions, there was little pressure to abandon the static view. Ambiguity favored familiarity. A changing universe required not just new data, but a willingness to reinterpret what stability meant on the largest scales. In retrospect, the assumption appears fragile. It relied on limited observation and strong intuition, yet it influenced the form of the most successful theory of gravity ever written. This is not a failure of logic, but a reminder that intuition scales poorly. What feels stable locally may be unstable globally. What appears motionless may be balanced only because deeper forces are held in check. The still universe was never observed. It was preferred. And for a time, that preference was enough to shape the equations that define space-time itself. Expansion discovered after the fact. When Edwin Hubble measured the distances to galaxies, he found something incompatible with a static universe. The farther away a galaxy was, the faster it was receding. Space itself was expanding. The original equations predicted this behavior without modification. The extra term existed only to suppress it. Einstein reportedly abandoned the term after this discovery, believing its introduction had been an error. The observation did not arrive as a dramatic revelation. It emerged gradually from careful measurement and cautious interpretation. Astronomers had already noticed that the light from distant galaxies was shifted toward longer wavelengths. This redshift was initially ambiguous. It could be interpreted as motion, as an effect of gravity, or as something else entirely. What Hubble added was distance. By identifying certain stars whose intrinsic brightness was known, he could determine how far away these galaxies actually were. When distance was plotted against redshift, a pattern appeared. It was not subtle. It was systematic. Galaxies twice as far away were receding roughly twice as fast. There was no preferred direction. The effect was the same everywhere. This was not motion through space in the usual sense. It was the expansion of space itself, stretching the light as it traveled. This distinction matters because it changes the meaning of motion. The galaxies were not fleeing from a central point. There was no explosion in space. Instead, every region of space was moving away from every other region. From any galaxy, the same pattern would be observed. Expansion was not something happening within the universe. It was something happening to the universe. The equations of general relativity had allowed for this outcome from the beginning. Solutions describing expanding or contracting universes existed naturally. They did not require special assumptions or additional terms. The behavior emerged directly from the relationship between matter and geometry. The universe could not remain static without intervention. In this light, the added term appeared unnecessary. It had been introduced to prevent expansion, not because expansion was impossible, but because it was unanticipated. Once expansion was measured, the rationale for the term evaporated. The equations worked better without it. They aligned with observation. The universe behaved exactly as the unmodified theory predicted. Einstein's reported reaction reflects this shift. The term was seen as an artificial constraint, a correction imposed to satisfy expectation rather than evidence. Removing it restored the equations to their simplest form. The universe was no longer forced to be still. It was allowed to evolve. For a time, this seemed like closure. The mistake had been identified and corrected. The equations were vindicated. Observation had caught up with theory. The expanding universe became an established fact, incorporated into cosmological models and refined with better data. But this resolution was incomplete. Expansion alone did not determine the future of the universe. The equations still allowed multiple possibilities. Depending on the amount of matter and energy present, expansion could slow, stop, reverse, or continue indefinitely. At this stage, expansion was a behavior, not a destiny. The removal of the term did not erase its implications. It merely set them aside. The equations still permitted it. They simply no longer required it to match known data. The mathematical structure that allowed space to behave independently of matter remained intact. This is an important subtlety. Abandoning the term did not eliminate the idea that space itself could have properties. It only removed one specific manifestation. The deeper conceptual shift introduced by general relativity remained unchanged. Space-time was still dynamic. Geometry still mattered. The expansion discovered by Hubble validated the most counterintuitive aspect of the theory. It showed that large-scale change was not only possible, but real. The universe was not a static container. It was an evolving structure. This alone was a profound revision of human perspective. Yet the sense of finality was misleading. The data available at the time described expansion, but not its rate of change. The universe was observed to be growing, but whether that growth was slowing or accelerating remained unknown. The equation still had room to surprise. In hindsight, the abandonment of the term marked not an end, but a pause. The equations had been allowed to speak once, and they had been correct. There was no guarantee they would not demand something even stranger when observations improved. The term was gone, but the possibility it represented had not been resolved. It had simply retreated into the background, waiting for the next measurement to bring it back into focus. The return of the forbidden constant. Decades later, observations forced the term back into relevance. Measurements of distant supernovae showed that expansion was not slowing down. It was accelerating. Something was pushing space apart more strongly over time. The simplest explanation was the same mathematical term Einstein had removed. The equation demanded its return, not as a correction, but as a dominant feature of reality. At first, this result appeared implausible. If the universe began in a dense, energetic state, its expansion should gradually slow under the influence of gravity. Matter attracts. Over time, that attraction should reduce the rate at which space stretches. This expectation followed directly from experience and from the behavior of the equations without the additional term. The supernova measurements contradicted that expectation. These stellar explosions act as reliable markers of distance because their intrinsic brightness can be inferred. By comparing how bright they appear to how bright they should be, you can determine how far away they are. Their light also carries information about how much the universe has expanded during its journey. When these measurements were combined, they revealed a consistent pattern. Distant supernovae were dimmer than expected. They were farther away than a decelerating universe would allow. The expansion rate had not been slowing, it had been increasing. This was not a subtle discrepancy. Independent teams using different methods reached the same conclusion. Systematic errors were examined and ruled out. The data held. The universe was accelerating. Within the framework of general relativity, this behavior requires a specific kind of influence. Ordinary matter cannot produce it. Gravity, as described by the equations, always acts to slow expansion when matter dominates. To reverse that trend, the equations require a component with negative pressure, something that contributes to the energy content of the universe while pushing outward rather than pulling inward. The previously discarded term does exactly this. It adds a uniform energy density to space itself. Its effect grows as the universe expands because more space means more total energy of this kind. The mathematics aligns cleanly. No additional assumptions are needed. The same term that once enforced stillness now explains acceleration. The return of the term was not a historical correction. It was a structural necessity. Without it, The equations could not reproduce the observations. With it, the behavior of the universe followed directly. The constant was no longer optional. It became essential. This reversal is unsettling because it reframes the original mistake. The problem was not that the term was artificial. It was that its role was misunderstood. It was introduced to suppress expansion, not to describe it. When expansion was first observed, it seemed safe to remove the term. But acceleration reveals that expansion alone was incomplete. The equations did not change. The interpretation did. What once appeared as a mathematical convenience became a physical requirement. The term was not correcting an error. It was revealing a property of space that had been present all along. This property is peculiar. Unlike matter or radiation, it does not dilute as the universe grows. Its density remains constant. As space expands, the total amount of this energy increases. This is not an approximation. It is a direct consequence of how the term is defined. From a measurement standpoint, this behavior is tightly constrained. The value of the constant can be inferred from multiple independent observations. Supernovae, the cosmic microwave background, and the distribution of galaxies. These measurements converge. The term has a specific, non-zero value. Conceptually, however, the situation is worse than before. The universe is not merely expanding. It is being driven apart by something that looks indistinguishable from empty space. The dominant influence on cosmic evolution is not matter, not light, but a property of space itself. This changes the narrative of cosmic history. Matter dominated the early universe. Structures formed, galaxies emerged, but as expansion continued, the influence of this constant grew. Eventually, it overtook everything else. The fate of the universe became controlled by something that cannot be localized or isolated. The return of the constant does not resolve the earlier discomfort. It amplifies it. The term is no longer a small correction introduced to preserve intuition. It is the central factor shaping the universe's future. The equations insist on its presence, and observation confirms its effects. What remains unexplained is why this term exists at all, and why it has the value that it does. Empty space that is not empty. You tend to think of empty space as nothing at all, but in these equations, space carries energy. This energy does not dilute as space expands. It remains constant per unit volume. As more space comes into existence, more energy appears. This is not a violation within the theory. It is a direct consequence of how the term behaves. This claim is difficult to accept because it contradicts how energy behaves in every familiar context. When matter spreads out, its density decreases. When radiation fills a larger volume, it weakens. Expansion usually thins things. Here, expansion does the opposite. It increases the total amount of energy by increasing the amount of space that contains it. The equations do not treat this energy as something stored in particles or fields that move through space. It is tied directly to the geometry of space itself. Wherever space-time exists, this energy exists. It cannot be isolated, shielded, or concentrated. It does not flow from one region to another. It simply persists uniformly. This uniformity is essential. If the energy varied from place to place, it would clump, interact, or produce observable structure. It does none of these things. Its effects are only noticeable on the largest scales, where the cumulative influence of expansion becomes measurable. Locally, it is negligible. Globally, it dominates. The idea that energy can be associated with empty space is not unique to cosmology. In quantum theory, even a perfect vacuum contains fluctuations. Fields cannot be exactly zero everywhere. There is always residual activity. However, when you attempt to calculate the energy of this vacuum using quantum methods, the result is vastly larger than what is observed cosmologically. This mismatch does not invalidate either theory. Both general relativity and quantum field theory work exceptionally well within their domains. The problem arises when you try to interpret the cosmological constant as vacuum energy. The numbers do not align. The predicted value exceeds the measured one by an enormous margin. The equations demand a tiny but non-zero value. Quantum theory offers a value that is catastrophically large. Despite this, the cosmological constant behaves exactly as if it were vacuum energy. Its pressure is negative. Its density is constant. Its influence grows as the universe expands. The resemblance is close enough that the interpretation is difficult to avoid, even if it remains unresolved. From the perspective of conservation laws, this behavior is unsettling. In everyday physics, energy conservation is strict. Energy cannot appear from nothing. But in an expanding universe, global energy conservation is not well defined. The equations conserve energy locally, but not necessarily across the entire spacetime. The increase in total energy does not violate the theory because the concept of total energy becomes ambiguous. This is not a loophole. It is a structural feature of general relativity. The theory does not provide a global accounting system for energy in a dynamic spacetime. As space expands, the bookkeeping changes. What you consider conserved depends on how you define the system. The consequence is that empty space becomes an active participant in cosmic evolution. It is no longer a background that merely hosts matter. It contributes directly to the dynamics of the universe. Its energy density determines how expansion proceeds and how the future unfolds. This redefinition alters your understanding of nothingness. Empty space is not the absence of physical influence. It is a state with measurable effects. Its properties are subtle, but their consequences are large. The acceleration of the universe depends on what appears to be nothing at all. The unsettling part is not that space has energy, but that this energy is unavoidable. You cannot remove it by removing matter. You cannot isolate a region of truly empty space. Even the deepest void between galaxies carries the same influence as every other region. As the universe expands, the relative importance of this energy increases. Matter becomes diluted. Radiation fades. Structures recede beyond observation. What remains is space and the energy it carries. The future universe is defined less by what it contains and more by the properties of the container itself. This behavior follows directly from the equations you already trust. No additional speculation is required. Empty space is not empty because the theory does not allow it to be. The contradiction is not that energy appears from nothing. It is that nothing was never truly nothing to begin with. A pressure that pulls things apart. Unlike matter or radiation, this energy exerts negative pressure. Instead of pulling inward, it pushes outward. The more space there is, the stronger its effect becomes. This leads to a feedback loop where expansion creates more space, which increases the total energy driving expansion. The universe accelerates not despite emptiness, but because of it. Pressure is usually associated with contact. Gas presses on the walls of a container. Radiation pushes by, transferring momentum. In these cases, pressure resists compression. It does not create expansion on its own. Negative pressure behaves differently. It acts as a tension rather than a push, a tendency for space to stretch rather than contract. In general relativity, pressure is not a secondary detail. It contributes to gravity in the same way energy density does. Both determine how space-time curves. For ordinary matter, pressure adds to gravitational attraction. High pressure intensifies collapse. This is why massive stars can implode when their internal pressure can no longer resist gravity. The energy associated with empty space reverses this relationship. Its pressure is negative and equal in magnitude to its energy density. This specific balance produces a repulsive gravitational effect. Instead of slowing expansion, it accelerates it. The equations do not treat this as an exception. It is a direct consequence of how energy and pressure enter the geometry of space-time. This behavior has no everyday analog. You do not encounter materials that become more influential as they spread out. You do not observe systems where expansion strengthens the cause of expansion. Yet this is precisely what the equations describe on cosmic scales. The feedback loop is subtle. As the universe expands, the volume of space increases. Because the energy density remains constant, the total amount of this energy increases with volume. More energy means a stronger effect on space-time curvature. Stronger curvature means faster expansion. The process reinforces itself. This does not lead to explosive instability. The acceleration is gradual, governed by a constant that is small in absolute terms, but over billions of years, the effect accumulates. What begins as a minor correction becomes the dominant influence on cosmic evolution. From the perspective of measurement, this negative pressure is not inferred indirectly. It is encoded in how the expansion rate changes over time. The acceleration of distant galaxies, the pattern of temperature fluctuations in the cosmic microwave background, and the growth rate of large-scale structures all point to the same conclusion. Something with this precise pressure-to-energy ratio is present. This precision is important. If the pressure were slightly different, the expansion history would change. Structures might not form. The universe could expand too quickly for galaxies to assemble, or too slowly to match observed distances. The observed value sits within a narrow range compatible with what you see. The negative pressure also reshapes the concept of gravitational attraction. Gravity is no longer universally attractive. Depending on the type of energy present, gravity can repel. This does not violate the theory. It fulfills it. The equations allow gravity to act in multiple ways, depending on the properties of the source. This realization undermines a long-held assumption. You expect gravity to pull things together. That expectation comes from experience with matter. On cosmic scales, with different forms of energy, the behavior changes. The universe expands faster because of a component that does not behave like anything you encounter locally. The acceleration has consequences beyond motion. It alters causality. As expansion speeds up, regions of space become increasingly isolated. Signals emitted now may never reach certain destinations. The structure of space-time changes in a way that limits what can influence what. This is not a future scenario imposed by speculation. It is a trajectory derived from current measurements. The universe is already in this accelerated phase. The negative pressure is already shaping what can be observed and what cannot. The unsettling aspect is that the driver of this process is featureless. It has no structure, no variation, no interaction beyond its gravitational effect. It does not announce itself through radiation or particles. It reveals itself only through the geometry of space and the motion of distant galaxies. You are left with a universe whose expansion is driven by the absence of things rather than their presence. The pressure that dominates cosmic evolution does not arise from matter pressing outward, but from space itself resisting being confined. The equations do not treat this as strange. They treat it as inevitable. A measurement without a source. You can measure the effects of this energy precisely. It alters the expansion rate of the universe. It shapes the large-scale distribution of galaxies. It leaves signatures in the cosmic microwave background. Yet it has no identifiable source. It does not clump. It does not interact. It simply exists wherever space exists, including where you are now. This is an unusual position for a physical quantity. Most things you measure can be traced to something localized. A star emits light. A mass bends space-time. A field has a source or a boundary. In this case, there is no object to point to, no region where the effect originates. The influence is uniform and pervasive. The measurements themselves are indirect but consistent. By tracking how fast galaxies recede at different distances, you can reconstruct how the expansion rate has changed over time. The pattern demands an accelerating phase. By examining the cosmic microwave background, you can see how sound waves moved through the early universe. Their imprint reveals the geometry of space and the energy components that shaped it. By mapping the distribution of galaxies, you can observe how structures grew and how their growth slowed. Each of these observations points to the same conclusion. A component exists that influences expansion but resists clustering. It does not gather into galaxies or halos. It remains evenly spread, unaffected by gravity in the way matter is. This uniformity is not an assumption. It is a requirement imposed by the data. If the energy clumped even slightly, its gravitational influence would distort the cosmic microwave background in ways that are not observed. If it interacted with matter or radiation, it would leave detectable signatures in particle physics experiments or astrophysical processes. None are seen. The energy reveals itself only through its global effect on spacetime. This absence of interaction complicates interpretation. You cannot probe it in a laboratory. You cannot isolate it in a detector. You cannot shield yourself from it or concentrate it for study. Its presence is inferred solely from how the universe behaves as a whole. This makes the energy difficult to categorize. It is not dark matter, which clumps and influences structure formation. It is not radiation, which redshifts and fades. It is not a force in the traditional sense, because it does not mediate interactions between objects. It is a property of space itself. The fact that it exists everywhere, including in regions devoid of matter, means that it is present in the space around you. Its density is extremely small. Locally, its influence is negligible. The gravitational pull of Earth, the Sun, and the galaxy overwhelms it completely. But its uniformity ensures that, on large scales, it cannot be ignored. This creates a disconnect between perception and measurement. You do not feel this energy. You do not observe its effects in daily life. Yet its influence determines the long-term behavior of the universe. The largest structures you can observe are shaped by something that has no observable structure of its own. The lack of a source also challenges causal reasoning. In physics, effects typically follow causes. Here, the effect is clear, but the cause is abstract. The equations include a term. The term produces an effect. The origin of the term is unspecified. The theory remains silent on why it exists. This silence is not a flaw in measurement. It is a gap in understanding. The data constrain the behavior of this energy tightly. They do not explain its nature. The equations accommodate it without illuminating it. you are left with a component of reality that is defined entirely by its consequences. It cannot be seen, touched, or manipulated. It does not announce itself except through the expansion of space. It is present in every region, but anchored to none. This situation reverses the usual hierarchy of explanation. Instead of identifying a thing and studying its effects, you observe effects and infer the existence of something that cannot be directly accessed. The energy is real because the measurements demand it. Its lack of a source does not make it optional. The unsettling implication is that a fundamental driver of cosmic evolution operates without a mechanism you can examine. It exists because space exists. The equations accept this without protest. Observation confirms it without exception. The absence of a source does not weaken the conclusion. It sharpens it. The smallest number, with the largest consequence. The value of this constant is extremely small. Compared to the energy of particles or stars, it is negligible. But because it fills all of space uniformly, it dominates the universe over time. This balance is so delicate that changing the value slightly would prevent galaxies, stars, or chemistry from forming. The universe exists in a narrow window defined by this term. On any human scale, the magnitude of the constant is almost irrelevant. In your room, the energy density it represents is dwarfed by the mass of the air, the walls, the furniture. It does not influence your movements or the objects around you. Its effects are imperceptible locally. Yet on cosmological scales, where distances are measured in millions of light years and the total volume of space is immense, the consequences accumulate. What seems small in isolation becomes dominant when multiplied across the universe. This duality, insignificant locally, overwhelming globally, forces a reconsideration of scale in physics. You are accustomed to associating importance with magnitude. The sun exerts force, a planet contains energy. But here, the quantity is minuscule, yet its influence surpasses that of every star, galaxy, and cluster combined. The universe's fate hinges on something you cannot detect with ordinary instruments, something that does not clump, radiate, or interact. The precision of the value is remarkable. A slightly larger or smaller constant would lead to catastrophic consequences. Increase it modestly, and the accelerated expansion would have prevented matter from collapsing into galaxies. Stars would never ignite. Chemistry, as you understand it, would not exist. Decrease it, and expansion would slow too rapidly. Gravity would dominate, potentially triggering a collapse before life could emerge. The observable universe emerges only within this narrow range. This sensitivity suggests a profound fine-tuning. It is not a general feature of physical constants. Most constants, such as the charge of the electron or the speed of light, do not control the global structure of space-time so directly. This one number governs the large-scale destiny of the cosmos. Small adjustments, imperceptible locally, determine the existence of all structure. Observationally, the constant's influence is visible in multiple ways. It shapes the accelerating expansion of galaxies, determines the curvature measured in the cosmic microwave background, and constrains the formation and evolution of large-scale structures. Models of the universe that omit or misestimate its value fail entirely. The simplest observation, the relationship between distance and redshift, cannot be reproduced without it. The universe behaves precisely as if this constant exists, with the measured magnitude nowhere more obviously than in the interplay between expansion and structure formation. Yet, despite its critical role, the origin of the number remains unexplained. There is no physical mechanism that predicts its value a priori. It exists as a parameter to be measured, not derived. The universe obeys the laws of physics you understand, but the existence of life and structure depends on a number that the equations allow but do not constrain. It is a constant in name and a mystery in essence. This reality introduces a conceptual tension. You can predict its effects, yet you cannot explain them from first principles. You can trace the acceleration of galaxies, the formation of stars, the arrangement of clusters, and the propagation of light across billions of years, all of which depend on this constant. Still, the reason the universe settled on this specific value is unknown. Its smallness is both a requirement for existence and a puzzle for understanding. In this sense, the constant is paradoxical. It is insignificant and dominant simultaneously. It is measurable, yet causally opaque. It shapes the universe profoundly while remaining invisible locally. The cosmos exists in a narrow window precisely because of this single number, and the delicacy of that window suggests that the universe's present state is not arbitrary, but contingent, balanced on a term that occupies no space in ordinary experience, yet defines all of cosmic history and future. A coincidence that has no explanation. You live at a moment when the energy of matter and the energy of space are comparable in magnitude. Earlier, matter dominated. Later, space will dominate completely. This overlap occurs briefly on cosmic timescales. The equations allow it, but they do not explain why you observe the universe during this transition. The timing appears arbitrary, yet unavoidable. From the perspective of cosmic history, this balance is fleeting. Matter, composed of stars, gas, and dark matter, controlled the expansion of the universe for billions of years. Its gravitational influence slowed the rate at which space stretched. Galaxies formed, stars ignited, and chemistry unfolded. This era produced the structures necessary for observers like you to exist. Without it, the universe would have remained a featureless void, or collapsed before complexity could emerge. Now, the energy of space, the constant that drives acceleration, has caught up. Its influence is no longer negligible. It competes with matter for control over cosmic expansion. The universe is neither purely matter-dominated nor fully in the grip of acceleration. It is in transition. The acceleration is measurable, yet not yet overwhelming. Structures remain intact, galaxies remain bound, and light still propagates through a coherent cosmic web. This temporal coincidence is striking because it is temporary. On scales of billions of years, it occupies only a narrow window. Earlier observers would have seen matter overwhelmingly dominant. Later observers, far in the future, would witness a universe almost entirely governed by the energy of space, with galaxies receding beyond view and local clusters isolated by the inexorable expansion. The moment you occupy is, in that sense, unique. The equations of general relativity permit this scenario, but they provide no reason for it. There is no mechanism that ties the emergence of observers to the epoch when the densities of matter and space are comparable. The universe could exist at any stage along the expansion curve, yet your presence coincides with this balance. The mathematics imposes no preference for when measurements are made. The effect is allowed, unavoidable, yet unexplained. Observationally, the significance is profound. The expansion history inferred from supernovae, galaxy surveys, and the cosmic microwave background confirms that the universe is in precisely this transitional phase. The accelerated expansion is detectable, but matter still dominates local gravitational dynamics. Galaxies remain gravitationally bound. The cosmic web remains intact. The interplay between the two forms of energy is critical for understanding the universe's structure as you see it. From a philosophical perspective, this coincidence is unsettling. It suggests that you are observing the universe at an exceptional moment, when the forces that govern large-scale evolution are roughly balanced. The universe does not provide a reason for this alignment. It is not an anthropic guarantee embedded in the equations. It simply exists, and you happen to observe it. This overlap also defines the universe's fate. The dominance of space is inevitable. Matter will become diluted as expansion continues. Stars will burn out. Galaxies will drift apart. And eventually, only isolated pockets of matter will remain within an ever-accelerating vacuum. The transitional period is brief, yet it is the era in which complexity persists. Its brevity heightens the sense of contingency. The coincidence challenges assumptions about naturalness and timing. Physics often seeks explanations for patterns, why constants take certain values, why interactions behave in specific ways. Here, the timing of your observation is a pattern with no causal derivation. It is a consequence of the values of the constants themselves, yet why it occurs precisely now remains opaque. In this sense, the universe is both predictable and puzzling. The equations dictate the eventual dominance of space, yet they do not indicate when observers will measure the balance. You witness a fleeting equilibrium, a temporal intersection between competing energies that is mathematically inevitable, but temporally exceptional. This unexplained alignment shapes not only the universe you see, but the very conditions that make observation possible. The result is a quiet unease. The cosmos is ordered, lawful, and predictable. Yet your presence coincides with a rare transitional state that has no explanation beyond its occurrence. You exist at a crossroads in cosmic history, where matter and space share influence, and the universe, for a brief moment, is precisely as it must be for you to notice it. Quantum theory makes it worse. When you attempt to calculate this energy using quantum physics, the result is catastrophically wrong. The predicted value exceeds the observed one by more than 100 orders of magnitude. Both theories work independently. Both are tested relentlessly. When combined, they produce a contradiction so large it resists interpretation. Quantum field theory assigns energy to empty space because fields cannot be entirely zero. Even in a vacuum, fluctuations occur. Particles and antiparticles spontaneously appear and vanish. These processes contribute to what is called the vacuum energy. By summing these contributions across all possible modes, you arrive at an energy density that is enormous, far larger than anything observed cosmologically. Yet, observation is precise. The acceleration of the universe, the cosmic microwave background, and the distribution of galaxies all indicate a much smaller value. The discrepancy is immense, exceeding 100 orders of magnitude. To put that in perspective, it is not a small error or an adjustable fudge factor. It is a gulf so vast that conventional intuition fails. The predicted vacuum energy would curve space so violently that galaxies, stars, and even atoms could not exist. The universe you observe would be impossible. Both general relativity and quantum field theory are extraordinarily successful. General relativity explains gravitational phenomena from planetary orbits to black hole mergers. Quantum field theory predicts particle interactions with unparalleled precision, underpinning the Standard Model. The success of these theories is not in question. Yet their union in cosmology exposes a fundamental tension. The simplest extrapolation of quantum fluctuations conflicts violently with the measured expansion of the universe. attempts to reconcile the two highlight the strangeness of the situation. Modifying quantum theory to reduce vacuum energy undermines its predictive power. Ignoring it violates principles of relativity. Theories of quantum gravity remain speculative and incomplete. Every approach confronts the same stark fact. The energy of empty space cannot be derived naturally from quantum mechanics without producing a universe unlike the one we inhabit. This tension is sometimes called the cosmological constant problem, but that label understates the philosophical weight. It is not merely a numerical mismatch, it is a confrontation between two pillars of physics. The very frameworks that successfully describe the microscopic and macroscopic worlds refuse to align when applied to the simplest form of energy in the universe. The contradiction is unavoidable. The laws work independently, but clash when combined. From a measurement standpoint, this energy is real and constrained. Its magnitude is not speculative. Observations of supernova, the cosmic microwave background, and large-scale structure all converge on a value consistent with accelerated expansion. This value is tiny relative to quantum predictions. Theories cannot be dismissed. The universe insists on a small, constant energy density. Quantum theory predicts something enormous. The gap is not marginal, it is absolute. The implication is unsettling because it challenges assumptions about fundamental reality. You expect that the energy of empty space, like any physical quantity, should be calculable, predictable, and understandable. Instead, it is simultaneously real, measurable, and inexplicably small. The mathematics allows no intermediate answer. Either the universe would have exploded in its earliest moments, or it behaves exactly as observed. Reality selects the latter without explanation. This failure is not abstract. It matters for every model of cosmic evolution. Inflation, structure formation, and the ultimate fate of the universe all depend on the behavior of vacuum energy. The mismatch calls into question whether you fully understand the connection between matter, space-time, and the quantum fields that fill it. In effect, you are confronted with a universe in which two extremely successful frameworks produce mutually incompatible predictions when applied to the same phenomenon. One predicts an impossible magnitude of energy. The other constrains it to a value that allows galaxies, stars, and life to exist. Both are tested. Both are correct. Both are incompatible. The consequence is profound. The laws of physics, as you know them, are internally consistent only when considered separately. When you attempt to describe reality as a whole, space-time with quantum fields, their predictions diverge catastrophically. The contradiction is not a technical detail. It is an existential feature of the cosmos. It is a measurement that cannot be reconciled with source or explanation. Cancellation, without a mechanism. To reconcile theory with observation, the value must be fine-tuned to extreme precision. Enormous contributions must cancel almost perfectly, leaving behind a tiny remainder. No known process enforces this balance. The equations require it, but they do not provide it. The universe behaves as if an adjustment was made without leaving evidence of how. Quantum field theory predicts vacuum energies that are staggeringly large. Summing these contributions without correction yields values that would curve space-time so violently that structure, stars, and even atoms could not exist. Yet the observed cosmological constant is minuscule by comparison. To reconcile these scales, the enormous positive and negative contributions must cancel to an extraordinary degree, leaving behind precisely the tiny value that drives cosmic acceleration today. This cancellation is exacting beyond comprehension. A fractional mismatch of one part in 10 120, 10 would render the universe unrecognizable. Galaxies would never form. The delicate interplay of matter and radiation would be disrupted. Chemistry, the building blocks of complexity, would fail. Life itself depends on this invisible balancing act. The cosmos exists in a narrow corridor between collapse and runaway expansion, a corridor defined solely by this precarious cancellation. No mechanism is known to enforce this cancellation. There is no symmetry, no feedback, no law that naturally compels positive and negative contributions to sum to the required value. The equations of general relativity allow the tiny remainder to persist, but they do not explain why it does. Quantum theory dictates enormous vacuum energies. Gravity responds to energy as it finds it. The resulting match between observation and theory appears coincidental, imposed without cause. Attempts to explain it often invoke concepts that go beyond current understanding. Some propose that an unknown symmetry cancels vacuum energy almost exactly. Others suggest a multiverse, where universes with all possible values exist, and observers naturally find themselves in one where the balance permits structure. These ideas do not resolve the underlying issue. They shift the explanation elsewhere, but the universe you inhabit still exhibits the extreme precision without a known enforcing mechanism. Observationally, the universe behaves as if the cancellation is perfect. Accelerated expansion proceeds exactly at the rate dictated by the tiny remainder. Galaxies remain gravitationally bound where they should be. The cosmic microwave background matches predictions, and large-scale structure develops in accordance with models that assume the small constant. The success of these models relies entirely on this precise value. Any deviation would produce measurable discrepancies, yet none are observed. The lack of a mechanism introduces a philosophical tension. In physics, explanations are usually causal. Forces produce motion, fields produce energy, interactions produce effects. Here, the effect exists, measurable and influential, without an identifiable cause. The universe appears tuned to permit its own evolution, yet no process accounts for the tuning. The equations demand a number, and the cosmos delivers it, with no intermediate steps visible. This situation highlights the limits of inference in physics. You can measure the cosmological constant with exquisite precision. You can observe its impact on expansion, galaxy formation, and the cosmic web. You can calculate the enormous contributions predicted by quantum fields. But the link between these layers, why the sum produces the tiny remainder, is absent. Observation constrains the outcome, but explanation is missing. The cancellation is also dynamic. As the universe expands, the total energy of space increases. The small value of the constant must persist despite this growth. Any change in the balance over cosmic time would be detectable, altering expansion rates and structure formation. Yet the tiny remainder remains stable across billions of years. The equations allow this, but the cause of its stability is opaque. In this sense, the universe acts as if an adjustment has been made, perfect in its effect, yet leaving no trace of the mechanism. The balance is real, measurable, and essential, but entirely unexplained. You are left with a cosmos in which the laws of physics operate flawlessly, while the reasons for one of the most critical parameters are absent. The cancellation exists as a fact of reality, precise and indispensable, yet causally inaccessible, a silent requirement underpinning the evolution of everything you can observe. Geometry as destiny. Because this energy belongs to space itself, it defines the long-term fate of the universe. Expansion will continue forever. distant galaxies will slip beyond observation. Light emitted today will never reach certain regions. The observable universe will shrink, not because objects disappear, but because space between them grows too fast to cross. The distinction between local and global behavior is essential. Locally, galaxies remain bound by their own gravity. Stars orbit centers of mass. Planetary systems remain coherent. The familiar interactions you observe are unaffected by the accelerating expansion. Yet on larger scales, the structure of space-time dominates. Distances between clusters of galaxies increase at a rate that eventually exceeds the speed at which light can traverse them. The universe becomes divided into isolated islands. This outcome is a direct consequence of the geometry dictated by the cosmological constant. The energy that fills space exerts negative pressure, accelerating expansion. As volume increases, the total energy associated with space grows. Unlike matter or radiation, which dilute as the universe expands, this energy maintains a uniform density. Its influence is cumulative. Over time, it overwhelms the gravitational attraction between distant structures, stretching space in a way that isolates regions irreversibly. The process is gradual, almost imperceptible on human timescales. For billions of years, galaxies remain observable. Structures evolve slowly, stars form, and life emerges. Yet the trajectory is inevitable. As time progresses, the regions beyond local clusters recede more quickly. Signals emitted from these distant regions today will never reach other galaxies. The observable universe shrinks in terms of causal connectivity, even as physical space itself continues to grow. This raises a subtle tension between perception and reality. You perceive a vast universe filled with countless galaxies. Yet the long-term fate of that universe is dictated not by the movement of objects, but by the behavior of the fabric in which they exist. Geometry alone determines what can interact with what. Space-time is not a passive backdrop. It is the driver of causal structure and the ultimate arbiter of cosmic evolution. From a measurement perspective, this fate is encoded in the expansion rate. Observations of distant supernovae, baryon acoustic oscillations, and the cosmic microwave background constrain the magnitude of the cosmological constant. These measurements imply a persistent acceleration. They define the timescale over which distant galaxies vanish from view. The equations predict that this trend will continue indefinitely, creating a universe where the observable horizon gradually contracts, even as space itself grows without limit. The implications extend to information and communication. Light, gravity waves, and any signal traveling across these expanding regions will eventually fail to bridge the increasing distances. Civilizations, if they exist elsewhere, will become causally disconnected. The large-scale universe becomes a mosaic of isolated regions, each bound internally but inaccessible externally. The future is defined not by objects moving away, but by the stretching of the space that separates them. This scenario also reframes the concept of cosmological time. The expansion of space dictates which events can influence one another. Causality becomes horizon-limited. Regions once able to exchange information are separated irreversibly. What is observable today may never influence what exists billions of years hence. The universe's history is etched into its geometry, with connectivity diminishing as expansion accelerates. In this sense, the universe's destiny is written in the structure of space itself. The energy that fills it shapes not only motion, but the accessibility of regions, the limits of observation, and the evolution of interactions. The observable universe is shrinking even as the total volume grows, and this effect is inexorably tied to the properties of empty space. Your perspective is transient. The cosmic horizon you see today is temporary. Future observers, or the remnants of structures long after stars have burned out, will inhabit a universe where connectivity is fractured, where the observable patch is minimal. The ultimate fate is inscribed in the geometry of space-time, driven by the energy of space itself, a deterministic path defined not by matter, but by the fabric in which all matter resides. Horizons that are not boundaries. There will be regions of space that exist but are causally disconnected from you. No signal can travel between them, not due to obstacles, but due to expansion. These horizons are not edges. They are consequences of geometry. The equations predict them precisely, and observation supports their existence. You tend to think of space as continuous and accessible, where signals propagate freely, where light eventually reaches its destination. On local scales, this intuition is correct. Photons travel across interstellar distances. Radio waves traverse planetary systems. Gravity exerts influence across light years. Yet on cosmological scales, the situation changes. Space itself is stretching, and this stretching can outpace the speed of information. The farther away a region is, the more quickly it recedes relative to you. Beyond a certain point, no signal, no influence can ever bridge the gap. These horizons are not physical barriers. There is nothing preventing travel in the conventional sense. No wall blocks light. No medium absorbs information. Instead, the expanding fabric of space-time ensures that objects move away from one another faster than light can traverse the intervening distance. Causality is limited not by local physics, but by global geometry. The horizon is a product of the rules that govern the universe itself, and it emerges inevitably from the presence of energy in space. The scale of these horizons is immense. Galaxies currently visible will eventually cross them. Clusters will drift apart. Signals emitted today from sufficiently distant regions will never reach you. Observation confirms that the expansion is accelerating, which implies that more regions will fall beyond causal reach over time. The universe becomes a patchwork of isolated domains, each internally coherent but externally unreachable. This phenomenon challenges the ordinary concept of a universe as a single, fully observable entity. You cannot perceive everything that exists. Regions beyond your horizon are just as real as those within it. They obey the same physical laws, yet you cannot interact with them. Existence is no longer synonymous with accessibility. Geometry dictates visibility, and visibility dictates the limits of causal influence. Horizons are not static. They evolve with time. As the universe expands, new regions recede past the horizon. Previously observable objects may cross the threshold of causal isolation, leaving only local structures within reach. The observable universe shrinks in terms of connectivity, even as the total volume of space continues to grow. The horizon is therefore dynamic, a moving boundary imposed by expansion itself. The mathematics describing these horizons is precise. The Friedmann equations, incorporating the cosmological constant, define how quickly regions recede and at what distances causal disconnection occurs. Observational data, from distant supernovae to the cosmic microwave background, confirms that the acceleration of expansion is real and consistent with the predicted horizons. The universe behaves exactly as the equations forecast, with no ambiguity about which regions are causally linked and which are forever beyond influence. The presence of horizons also reframes the concept of information in the universe. Causal disconnection implies that events in some regions cannot influence your local measurements. Observations of distant galaxies, the propagation of light, and the growth of structure are all confined within the horizon. Anything beyond it exists independently, unaffected by your region, and unable to affect you. The universe, in this sense, is partitioned not by matter or energy, but by the geometry of space itself. This reality is quietly unsettling because it undermines the intuitive assumption that the cosmos is fully accessible. Horizons are not walls. They are mathematical consequences of the expansion driven by the energy of empty space. The observable universe is only a subset of what exists. The rest persists, unreachable, causally irrelevant. It is a realm that is real yet invisible, defined entirely by the structure of space-time. Your perception is therefore limited in an intrinsic, unavoidable way. The laws of physics allow regions to exist beyond observation. They impose boundaries not through obstacles or destruction, but through the relentless expansion of space. The horizons are neither artificial nor arbitrary. They emerge inevitably from the combination of geometry, energy, and time, a silent architecture that constrains what can ever interact, communicate, or influence, leaving vast swaths of reality forever beyond reach. A universe that erases its own evidence. As expansion accelerates, the signals that reveal cosmic history fade. The background radiation cools beyond detectability. Galaxies disappear from view. The future universe becomes observationally empty. The equations imply that knowledge of cosmology is temporary, available only during a limited era. You tend to assume that the universe's history is permanent, recorded in stars, galaxies, and the radiation that fills space. This assumption is valid today. The cosmic microwave background provides a snapshot of the early universe. Galaxies trace the growth of structure. Light traveling across billions of years carries information about expansion, composition, and geometry. Yet the mathematics that governs space-time predicts a future in which these records vanish, not because they are destroyed, but because they are carried beyond reach. The cooling of the cosmic microwave background is a direct consequence of expansion. As space stretches, photons lose energy, shifting to longer wavelengths. Eventually, the radiation redshifts beyond detection by any conceivable instrument. The echo of the universe's origin fades into obscurity. Even the most precise measurements today will be meaningless in a future dominated by accelerated expansion. The signature of the Big Bang, once evident in every corner of space, becomes undetectable. Galaxies themselves recede at ever-increasing velocities. Those not gravitationally bound to your local cluster drift beyond causal contact. Their light never reaches your vantage point. Structures that currently provide evidence of cosmic history will vanish from observation. The web of interactions that allows measurement of expansion, mass distribution, and evolution dissolves. Space remains populated, but the ability to know its contents evaporates. This process implies a temporal horizon for knowledge. Observation of the universe as a coherent system is contingent on timing. Today, you can see distant galaxies, measure redshifts, and infer the balance between matter and dark energy. 1 billion or more years in the future, these methods will fail. Observers in such an era will inhabit a universe that appears static, unchanging, and devoid of history. The universe itself erases the evidence of its dynamic past. The implications extend to the concept of causality and inference. The equations predict that physical laws remain, but the empirical traces required to understand them are gone. Without the light from distant objects, the cosmic expansion history cannot be reconstructed. Without the microwave background, the primordial conditions remain hidden. Observational cosmology becomes impossible, not due to limits of technology, but because the structure of space-time ensures that evidence recedes beyond access. This erasure is gradual, yet inevitable. Acceleration grows as space expands. The energy driving it, the cosmological constant, remains uniform. The farther apart objects are, the faster they recede. The cumulative effect over billions of years ensures that every photon from unbound structures is stretched beyond detectability. The future is populated with objects, but they exist in isolation, unreachable, their existence inferred only by the equations, not by observation. The phenomenon also challenges intuition about permanence. You expect that what exists now has always existed and will always be knowable. The universe contradicts this. Knowledge of its history, the distribution of matter, the evidence of cosmic evolution, is ephemeral. The laws of physics do not disappear, but the ability to connect theory with observation vanishes. Cosmology is a science constrained not only by measurement, but by the era in which measurement is possible. Even your local cluster is insulated. Light from beyond will never enter it. Observers within bound structures will witness a universe that appears unchanging, a silent expanse that provides no clues about what lies beyond. The dynamic history, visible today across billions of light years, becomes hidden in a future dominated by accelerated expansion. This inevitability is encoded in the geometry of space-time. The presence of energy in space, uniform and constant, ensures that expansion accelerates perpetually. Observational access diminishes steadily. The universe gradually transforms from a rich, observable cosmos into a patchwork of isolated, uncommunicative regions. Evidence disappears not by destruction, but by the relentless stretching of the fabric that carries it. You are witnessing a moment when observation is possible. Galaxies, radiation, and cosmic structures provide measurable clues. In a future dominated by space itself, all of that will fade. The universe erases its own evidence, leaving a landscape where existence continues, but knowledge cannot. Observation is transient. Knowledge is provisional. The cosmos contains everything, yet reveals only what the era allows. The illusion of stability. On human scales, none of this is perceptible. Your room does not stretch in any meaningful way. Atoms remain bound. Local forces dominate. This hides the global instability of space. The universe appears static where it matters to you, even as its large-scale behavior is governed by an accelerating expansion. Gravity, electromagnetism, and the strong and weak nuclear forces maintain order on familiar scales. Planets orbit stars. Air molecules interact within the room. The binding of atoms and the rigidity of solid objects counteracts any influence from the expansion of the universe. The stretching of space is too small to affect such tightly bound systems. Your immediate experience is insulated from cosmic change, yet the apparent stability is deceptive. The accelerating expansion acts relentlessly on scales beyond local gravitational or electromagnetic binding. Galaxy clusters are carried apart. Light from distant regions becomes redshifted to invisibility. The fabric of space grows, and with it, the causal relationships that define the observable universe shift. The stability you perceive is a local artifact, a small-scale illusion imposed by the relative strength of forces in your environment. This illusion reinforces a false intuition about permanence. You assume that what is will remain perceptibly the same. The room, the house, the street, all appear static. From this perspective, the universe seems unchanging. Yet beyond this scale, the geometry of space-time evolves inexorably. Objects that seem fixed in space are not immune to the expansion. They are simply bound tightly enough that the effect is imperceptible for now. The difference between local and global scales is not merely quantitative, it is qualitative. Local forces create a self-contained region of apparent stability. The cosmic expansion, driven by the energy of space itself, exerts influence only where binding forces are insufficient to dominate. The equations of general relativity treat all regions of spacetime equivalently, but the observable effects differ dramatically depending on the scale and density of matter. What seems static in one region may be accelerating uncontrollably in another. This dissonance between perception and reality has consequences for understanding the universe. If you were to extrapolate your local experience, you would assume that the cosmos is static and eternal. Observations on larger scales contradict this assumption. The redshift of distant galaxies, the cooling of the cosmic microwave background, and the accelerated expansion revealed by supernovae demonstrate that the universe is dynamic. Stability is an emergent, localized phenomenon, not a global property. Even within bound systems, subtle effects persist. Tidal forces, gravitational lensing, and orbital dynamics carry the imprint of a universe that is not static. The motions of clusters and the growth of large-scale structure are influenced by the expansion of space, even if imperceptibly in daily life. Your immediate perception does not register these effects, but the mathematics accounts for them, revealing a universe whose stability is provisional and relative. This local insulation creates a temporal perspective that is misleading. The apparent, unchanging nature of your surroundings is valid over human timescales, but fails over cosmic durations. Billions of years in the future, even the observable patch around you will differ dramatically. Regions currently visible will recede beyond causal contact. The small-scale stability that defines your perception today cannot be extrapolated to the universe as a whole. The illusion also shapes assumptions about causality and determinism. You perceive interactions as continuous and bounded, as if space were a constant backdrop. In reality, space-time itself is dynamic, influencing the evolution of objects and the propagation of information. Local stability hides a universe in which geometry dictates connectivity, isolation, and the eventual erasure of evidence. Your intuition is therefore both reliable and misleading. On scales familiar to experience, the universe behaves predictably. On cosmic scales, this predictability dissolves. The accelerating expansion of space ensures that stability is an emergent, temporary phenomenon. What you perceive as permanent is contingent, confined to the small-scale forces that dominate your immediate environment. Beyond these boundaries, the universe evolves according to laws that are imperceptible yet inexorable, quietly reshaping reality far beyond what your senses can detect. In this sense, the universe presents a dual nature, locally static, globally dynamic. The stability you inhabit is a temporary refuge. Beyond it, space-time stretches, structures drift apart, and horizons emerge. The apparent permanence of your surroundings obscures the fundamental instability that defines the cosmos itself, a reality dictated not by matter or motion, but by the geometry and energy of space. Removing the constant breaks reality. If you remove the term again, the equations no longer match observation. The universe would decelerate. Structures would form differently. The cosmic background would not align with measurements. The term cannot be discarded without discarding accuracy. What was once considered a mistake is now required. In the original formulation, Einstein introduced the term to enforce a static universe. Observationally, this was unnecessary once Hubble measured the expansion of galaxies. The term appeared superfluous and artificial, a mathematical crutch rather than a reflection of reality. Yet when confronted with late-time accelerated expansion, the same term became essential. Removing it produces predictions incompatible with what you measure. The universe, mathematically speaking, cannot evolve correctly without it. Without the constant, the expansion rate would slow under the influence of gravity alone. Galaxies would continue to form, clusters would merge, and structures would develop more densely than observed. The cosmic web would differ in scale and connectivity. The patterns in the cosmic microwave background would not match the acoustic peaks detected in precise measurements. The geometry and dynamics of space, as encoded in general relativity, demand the constant to produce the universe you see. This requirement underscores a profound tension between intuition and necessity. The term was invented to enforce a conceptually desirable outcome, a static cosmos. Later, it was abandoned because that outcome was empirically false. Now, decades later, the universe itself reasserts the term's relevance. What was once a convenience has become a principle. The equations, the observations, and the structure of spacetime all converge to insist on its inclusion. The universe requires the term, not as an option, but as an inevitability. Its presence affects every scale. Locally, you are insulated from its influence. Atoms, planets, and galaxies are bound by gravity, electromagnetism, and nuclear forces. Yet on cosmological scales, it dictates expansion. Light from distant galaxies redshifts according to its value. Large-scale structure develops in a manner consistent with the balance between gravitational attraction and repulsive acceleration. The term integrates the microscopic and macroscopic, constraining the universe's evolution while remaining imperceptible in your immediate experience. Observations reinforce this necessity. Supernovae at cosmological distances trace the acceleration of expansion. Measurements of baryon acoustic oscillations confirm the large-scale geometry predicted by the constant. The cosmic microwave background provides a detailed record of how the universe evolved from its earliest stages. Every dataset independently points to the same conclusion. The accelerating expansion cannot be modeled accurately without the term. Its removal produces contradictions at multiple levels simultaneously. The constancy also interacts with other components of the universe. Matter, radiation, and dark energy co-evolve. Removing the term disrupts this balance. Galaxies would form too quickly. The background radiation would cool differently, and the timing of structure formation would conflict with observed ages of stars and clusters. The term is not an arbitrary addition. It is integral to the coherence of cosmic evolution. This has philosophical consequences as well. What was once considered a mathematical convenience, a mistake, becomes a defining feature of reality. The universe exhibits a form of rigidity, where certain elements are required to preserve consistency across time and scale. The energy of empty space is no longer optional. It is embedded in the structure of spacetime. Removing it is not merely an adjustment, it is a violation of observational truth. In effect, the constant demonstrates that the universe is less malleable than intuition suggests. It highlights a tension between simplicity and correctness, between what seems natural and what is necessary. The equations of general relativity, combined with observation, dictate the inclusion of a term once repudiated. Accuracy demands what was once considered an error. The consequence is quietly unsettling. A feature of the equations, dismissed for decades as artificial, now defines reality. The structure, expansion, and observable history of the universe rely upon it. Its presence is unavoidable. To discard it is to discard the universe as you know it. What was once a mistake is now not only required, but essential, a mathematical truth imposed by the cosmos itself, defining the evolution of space, time, and structure in a way that no alternative formulation can reproduce. Adding it breaks. Understanding, yet including it, introduces deep conceptual problems. Energy conservation becomes ambiguous. The origin of the value remains unexplained. The relationship between quantum fields and space-time geometry collapses into inconsistency. The equations work, but the explanation does not. In classical physics, energy is a conserved quantity. It can be transferred, transformed, or stored, but the total remains fixed. With the cosmological constant, this principle becomes murky. The energy associated with empty space is constant per unit volume, but as space expands, the total energy increases. There is no reservoir from which this energy is drawn. It appears spontaneously, everywhere, as more space comes into being. The usual notion of conservation no longer applies in a straightforward sense. Energy exists, affects the dynamics of the universe, but its bookkeeping defies traditional understanding. The origin of the value itself is equally perplexing. Quantum theory predicts enormous vacuum energies. General relativity allows a cosmological constant. Observation shows a value that is staggeringly small compared to what quantum fluctuations suggest. Why the universe chose this number remains unknown. No law constrains it. No symmetry explains it. Its presence is required for structure, yet it appears as a free parameter, inexplicable and finely tuned. It is a number you can measure but cannot derive, a feature that simultaneously enables the universe and defies comprehension. The tension between quantum fields and space-time geometry deepens the problem. Quantum fluctuations suggest energy densities that would warp space-time catastrophically. Gravity responds to energy, so naively adding all contributions should produce a universe vastly different from the one observed. The small observed value of the cosmological constant implies an almost perfect cancellation of enormous contributions, but no known mechanism enforces this. The equations remain consistent. The universe behaves correctly. Yet the underlying reason for the delicate balance is absent. Physics succeeds in prediction, but fails in explanation. Including the term also undermines intuitive causality. Normally, energy and motion are linked. Energy generates force, force produces motion, and motion redistributes energy. The cosmological constant, however, is energy without source, pressure without material carrier. It acts globally, accelerating expansion everywhere simultaneously, yet it interacts with nothing in a conventional sense. The universe responds as if a force exists, but there is no particle, no field, no medium to account for its influence. The mechanism is invisible, yet its effects dominate the largest scales. This inclusion creates an epistemological problem. Observation constrains the value, yet theory provides no satisfying derivation. Calculations predict too much, intuition expects nothing, and reality sits between, exactly at the measured value. The universe behaves according to laws you understand, yet the fundamental reasoning behind one of the most consequential components is missing. It is an explanatory gap that cannot be bridged by current physics. The implications for cosmology are profound. Models of the universe rely on the term for consistency with supernova observations, the cosmic microwave background, and large-scale structure. Predictions work with the constant, but your understanding of why they work fails. You can simulate the evolution of galaxies, clusters, and cosmic expansion accurately, yet the cause of the driving energy is opaque. The equations succeed where insight falters. Even the long-term evolution of the universe is entwined with this ambiguity. The constant ensures accelerated expansion, determines horizons, and dictates which regions will become causally disconnected. It governs the eventual erasure of observable evidence. Without it, predictions fail. With it, explanations collapse. The universe exists in a narrow balance where inclusion is required, but understanding is compromised. Ultimately, the cosmological constant exemplifies a paradox of knowledge. The universe obeys precise laws, yet one of its most influential parameters resists derivation. The inclusion of the term produces results that align perfectly with observation, yet simultaneously exposes a fracture in comprehension. You can measure, model, and predict, but the why remains inaccessible. The equations function flawlessly, yet understanding falters. The cosmos is coherent in practice, incoherent in explanation. Inclusion solves prediction, but breaks understanding. A parameter that is not derived. Most physical constants are measured, then explained through deeper theory. This one is measured and left untouched. It sits in the equations without justification. It does not emerge from symmetry or principle. It is simply there, shaping everything without revealing why. Other constants, like the speed of light, Planck's constant, or the gravitational constant, fit within theoretical frameworks that provide rationale for their values. They connect disparate phenomena, constrain interactions, and reveal underlying principles. Even when measured empirically, their role can be traced back to symmetry, conservation, or the mathematical structure of a theory. The cosmological constant does not behave in this way. Its value is inserted to match observation, with no deeper derivation from first principles. Quantum field theory suggests an enormous vacuum energy. General relativity permits a cosmological constant. Observation confirms a tiny positive value that drives accelerated expansion. Nothing within current theory predicts the magnitude. There is no symmetry, no invariance, no conservation law that necessitates its size. It is a number imposed by the universe, not derived from it. It exists as a free parameter, inexplicably tuned to allow galaxies, stars, and life to form. This leaves an unsettling asymmetry in your understanding of the cosmos. You can explain why planets orbit stars, why light bends near massive objects, why quantum fields fluctuate. Each process has a mechanism. The cosmological constant, in contrast, acts globally, influencing the entire universe, yet its origin is unanchored. It is both essential and arbitrary, a foundational feature whose cause is invisible. The equations succeed in prediction, yet fail to provide insight into the source or necessity of the parameter. Its arbitrariness also highlights the fragility of cosmic structure. Slight changes in its value would dramatically alter the universe. A larger constant would accelerate expansion so quickly that galaxies could not form. A smaller one would leave the universe dominated by matter, delaying the emergence of structure and leaving the long-term acceleration unobservable. The universe exists within a narrow window, defined solely by this unexplained number. Its magnitude is critical, yet fundamentally opaque. Attempts to rationalize the constant often invoke anthropic reasoning or multiverse scenarios. In these frameworks, the constant takes many values across hypothetical universes, and observers appear only in regions where its value permits complexity. While this explains the coincidence, it does not provide a physical derivation. The parameter remains unconnected to underlying laws. It is not predicted, it is selected. The universe behaves as if the constant were fundamental, yet its necessity arises without cause. The lack of derivation has implications for both cosmology and fundamental physics. The constant governs the ultimate fate of the universe, the structure of horizons, and the causal connectivity of regions across billions of light years. It controls the expansion rate, the growth of structure, and the conditions for observation. A single unexplained parameter determines phenomena across scales, from the microscopic influence of quantum fields to the isolation of distant galaxies. Measurement is precise, but explanation is absent. Observations constrain the value tightly, yet no mechanism provides the origin. The universe's behavior is therefore contingent upon a number that is empirically known, but theoretically mysterious. Its inclusion in the equations works flawlessly, yet offers no insight into why the cosmos behaves in the way it does. You can simulate expansion, predict horizons, and model the cosmic web, yet the reason for the constant's value remains hidden. In this sense, the cosmological constant is unique. It is a parameter that shapes everything yet explains nothing. It is measured, required, and observed, but its origin lies outside current theory. Physics can describe its consequences in exquisite detail, but it cannot account for its existence. The universe is contingent upon this unexplained feature. It is fundamental, invisible, and unavoidable, a constant that commands the behavior of all space, yet refuses derivation. Ultimately, the cosmological constant embodies the tension between prediction and understanding. It functions as a precise tool for modeling reality, yet it defies theoretical explanation. You can know its effects, measure its magnitude, and simulate its consequences. But the underlying reason it exists, the principle from which it emerges, remains absent. It is a number without derivation, a defining feature of the cosmos whose presence shapes everything while revealing nothing. Space, as an active participant. The constant forces you to abandon the idea that space is a container. Space becomes an actor with its own dynamics, capable of influencing matter without interaction. This redefinition is subtle, but profound. It alters how causality and locality are understood on cosmic scales. Traditionally, space is imagined as a passive stage. Matter moves, light propagates, and forces act within a fixed background. You experience this daily. Rooms hold objects, planets orbit stars, photons travel in straight lines unless deflected by gravity. In these scenarios, space is inert. It is a backdrop, a coordinate system that allows motion to occur, but does not itself contribute to the evolution of the universe. The cosmological constant challenges this assumption entirely. In the presence of the constant, space behaves as a dynamic entity. Its energy density produces pressure that drives the acceleration of expansion. Matter does not push it apart, nor does it pull against it. Space itself expands, stretching distances between structures, shaping the observable universe, and dictating the ultimate isolation of causally disconnected regions. The force you attribute to gravity is countered, on the largest scales, by the energy intrinsic to space itself. Space is no longer a container. It is a participant, with measurable influence over the motion and connectivity of matter. This reconceptualization has immediate implications for causality. Traditionally, cause precedes effect, and interactions are mediated locally through forces or signals traveling at finite speeds. Accelerated expansion, driven by energy inherent to space, modifies this framework. Objects recede not because of motion through space, but because the space between them grows. Light emitted from distant galaxies will never reach you. not due to obstruction or absorption, but due to the inexorable expansion of space itself. Causality becomes limited by the dynamics of the medium, not simply by the propagation of signals within it. The effect is cumulative and global. The energy of space pervades all of existence, uniform across distance. Its influence increases with scale, dominating over gravity in sparse regions between galaxy clusters. Locally, bound systems remain stable. Stars orbit, planets spin, molecules vibrate. But as you examine the universe at scales spanning hundreds of millions of light years, the active role of space emerges. It dictates the structure of horizons, the evolution of large-scale clusters, and the eventual erasure of observable information. Space participates in shaping the observable universe independently of matter. This also challenges the concept of locality. Traditional physics assumes that interactions are transmitted across space. Gravity propagates at finite speed, electromagnetic forces act over distances, and causally connected regions are defined by light cones. With space as an actor, the expansion driven by its energy modifies these connections. Regions that were once accessible drift beyond causal contact. Signals from galaxies that exist continue to propagate at light speed, yet the space between sender and observer expands faster. The universe becomes partitioned, not by barriers or obstacles, but by the activity of the substrate itself. Observation confirms this behavior. Measurements of supernovae, the cosmic microwave background, and the distribution of large-scale structure all reflect the influence of space's intrinsic energy. Accelerated expansion is precisely consistent with a universe in which the fabric of space is dynamic, pushing structures apart without a material intermediary. The equations predict this phenomenon exactly, and observation corroborates it. Space's activity is not speculative, it is measured. The conceptual consequences are profound. The universe can no longer be viewed as a static arena in which matter merely exists. Space contributes to the unfolding of events. It generates effects without particles or fields in the conventional sense, acting on scales that dwarf human perception. You are accustomed to thinking of emptiness as inert. Yet on cosmological scales, emptiness shapes motion, structure, and causal connectivity. In this sense, the cosmological constant transforms your understanding of reality. Space is no longer a passive container, but an active participant. It dictates how the universe evolves, how regions interact or become isolated, and how structures emerge or fade from observation. The substrate of existence is alive in its dynamics, influencing matter without touching it, shaping the cosmos in ways that defy everyday intuition. Your perception of empty space as nothingness is insufficient. On the largest scales, space is force, actor, and architect, guiding the destiny of the universe itself. Observation. Without interpretation. Astronomers measure expansion rates, redshifts, and background radiation with extraordinary precision. These observations are consistent. The contradiction lies not in the data, but in its meaning. The universe behaves exactly as described, yet the description resists coherence. When you examine the cosmos, every measurement reinforces the same picture. Space is expanding, the expansion is accelerating, and the energy of empty space dominates the dynamics on the largest scales. Supernovae reveal precise redshifts that trace this acceleration. The cosmic microwave background records fluctuations consistent with a universe governed by general relativity, plus a cosmological constant. Large-scale surveys map the distribution of galaxies in alignment with predictions. No observation deviates from expectation. The universe behaves exactly as the equations dictate, yet understanding lags behind measurement. The observations, though precise, defy interpretation in conventional terms. You can quantify the expansion, calculate the energy density of space, and predict the behavior of structures billions of light years apart. The data is internally consistent, repeatable, and coherent. And yet, when you ask why the universe behaves this way, when you seek a mechanism or principle behind the observations, there is no answer. The universe conforms to measurement, but explanation fails. This creates a peculiar tension between theory and observation. General relativity describes the dynamics of space-time accurately. Quantum mechanics governs the fluctuations of fields with unparalleled precision. The cosmological constant is measurable and required. The data aligns with every prediction, yet when you attempt to synthesize these frameworks, contradictions appear. Quantum calculations of vacuum energy are catastrophically larger than the observed value. Theories work independently, yet when combined, they resist coherent interpretation. Observation is consistent, understanding is not. The discrepancy affects how you conceptualize reality. You perceive a universe that evolves predictably according to well-tested laws. Accelerating expansion, red-shifted light, and the thermal history of the cosmos all fit within this framework. Yet the origin of the driving energy, the reason for its magnitude, and the reconciliation with quantum fields remain unexplained. Measurement offers certainty, while interpretation confronts you with ambiguity. You know what happens, but not why. Moreover, the universe itself imposes limits on interpretation. Horizons grow, galaxies recede, and evidence of past epochs diminishes. Observations that are possible today may be impossible in the far future. Knowledge is temporally constrained. Even as you gather precise data now, the universe's geometry guarantees that this information will eventually vanish from observation. Reality is accessible, yet transient, leaving interpretation tethered to a fleeting epoch. The problem is compounded by scale. Locally, physics operates as expected. Atoms interact, planets orbit, light travels. Cosmologically, space itself is dynamic, exerting influence without mediation. Observations detect these effects, yet intuition cannot accommodate them. The discrepancy is not in measurement. It is in reconciling familiar notions of causality, energy, and locality with the behavior of the universe at vast scales. The universe acts coherently, but conceptual frameworks strain under its implications. Even theoretical models illustrate the dilemma. Numerical simulations of structure formation reproduce the cosmic web with astonishing accuracy. Predictions for the cosmic microwave background match observation to minute detail. Expansion rates inferred from multiple independent probes converge precisely. Each dataset corroborates the others. Yet the underlying principles that produce this agreement, the fine-tuned cosmological constant, the balance of vacuum energy, the role of empty space as an active participant, remain unexplained. Observation is exact. Interpretation is provisional. Ultimately, this juxtaposition defines the cosmological paradox. You possess flawless data about expansion, structure, and the composition of the universe. Every observation supports a coherent mathematical framework. The universe behaves exactly as predicted, and yet understanding lags irretrievably behind. The equations work, the measurements confirm them, but the meaning, the connection between cause, principle, and existence, remains elusive. Observation is complete. interpretation incomplete. The universe is knowable in detail, yet simultaneously incomprehensible in origin. In this way, cosmology becomes a study of contradictions embedded in certainty. The universe reveals itself in measurements, yet conceals itself in meaning. You can map it, quantify it, and predict its evolution with precision. You cannot, however, explain why it is the way it is. Observation proceeds unimpeded, but interpretation falters. The cosmos acts with coherence, while understanding remains suspended, leaving the universe both fully measured and fundamentally enigmatic. The comfort of mathematical success. Because the equations work, the discomfort is easy to ignore. Predictions match observation. Models converge. The term becomes routine. But mathematical success does not imply conceptual clarity. The underlying tension remains, unresolved and largely unspoken. In practice, the cosmological constant fits seamlessly into the machinery of general relativity. Calculations incorporating it reproduce the observed expansion of the universe, the large-scale distribution of galaxies, and the detailed patterns of the cosmic microwave background. Simulations of structure formation yield results that align precisely with what astronomers measure. The equations are elegant, internally consistent, and empirically validated. This precision allows scientists to treat the term as a parameter in their models, something to be measured and applied rather than questioned. This creates a sense of reassurance. The universe can be described accurately using known laws. Observations are predictable. Predictions are confirmed. The term becomes routine, embedded in textbooks, simulations, and lecture notes. Its inclusion is uncontroversial in the day-to-day practice of cosmology. Researchers can model galaxy evolution, supernova distances, and cosmic expansion without pausing to consider the deeper implications of the constant. Success is tangible, measurable, and comforting. Yet beneath this comfort lies a profound conceptual tension. The equations succeed, but understanding does not follow. You can predict the expansion rate, model the causal disconnection of distant galaxies, and forecast the erasure of cosmic evidence billions of years in the future. Every simulation is internally consistent. Every measurement aligns with theory, and yet the origin of the term, its extraordinary fine-tuning, and its conflict with quantum field theory remain unexplained. Mathematical accuracy masks conceptual ambiguity. The ease of mathematical success also reinforces a kind of cognitive blind spot. Because the models function, the tension is rarely addressed in ordinary discourse. The term becomes a tool, not a problem. Its presence is accepted without scrutiny. Cosmologists focus on deriving consequences, calculating observable phenomena, and refining simulations. The fundamental paradox that a measured, unexplained energy dominates the universe and drives accelerated expansion remains largely unexamined in practical work. The universe behaves correctly, so discomfort can be deferred. This tension highlights a divide between empirical success and theoretical understanding. Observation confirms the expansion history, the cosmic web, and the growth of structures. Theory predicts these outcomes with precision. But the why, the mechanism, the principle, the origin of the cosmological constant remains inaccessible. You can simulate a universe with extraordinary fidelity, yet the cause of its accelerated expansion, the source of energy in empty space, cannot be derived from known physics. Success in prediction does not translate to insight. The dissonance also touches the nature of knowledge in cosmology. Measurement is finite. Observation, temporal, and explanation contingent. The universe allows you to quantify its behavior, yet the parameters necessary for that quantification resist derivation. The cosmological constant exemplifies this. It is both essential for accurate prediction and mysterious in origin. Its inclusion produces a universe that matches observation, yet the understanding of why it exists, why it has its precise value, and why it interacts with geometry in the way it does, remains beyond reach. Even the act of calculation provides a subtle illusion of completeness. Complex simulations, data analysis, and theoretical modeling yield precise results, reinforcing confidence in understanding. But what is understood is procedural, not explanatory. You can model accelerated expansion, reproduce the cosmic microwave background, and anticipate future horizon formation. You cannot explain the origin of the energy that drives these phenomena, nor can you reconcile it fully with quantum theory. The tension between success and comprehension persists quietly beneath the surface of calculation. Ultimately, the comfort of mathematical success is a double-edged phenomenon. It allows you to interact with the universe, to measure, simulate, and predict, while simultaneously obscuring the underlying conceptual void. Precision in equations creates a facade of understanding. Prediction succeeds, explanation does not. The tension, unresolved and largely unspoken, remains an enduring feature of cosmology. Even as models converge and observations align, the universe retains a dimension that eludes comprehension. A cosmos perfectly described by equations, yet fundamentally enigmatic in its meaning. A universe balanced on absence. The dominant component of the universe is not matter or radiation, but something indistinguishable from empty space. Its influence grows as everything else thins out. The future is governed not by what exists, but by what does not. You are accustomed to thinking that the universe is shaped by tangible entities, stars, galaxies, planets, and the matter that constitutes them. Forces between particles, gravitational attraction, and the interactions of light and matter seem to determine the evolution of cosmic structures. Yet, on the largest scales, the universe is dominated by a form of energy that occupies space itself. It does not clump, it does not interact in any conventional sense, and it is invisible except through its effect on the expansion of space. What you perceive as empty is the most consequential component of reality. This energy does not dilute. As galaxies move apart and matter thins with expansion, the density of empty space remains constant per unit volume. Its effect becomes increasingly dominant as matter and radiation grow sparser. What begins as a subtle influence on cosmic dynamics eventually dictates the long-term evolution of the universe. The growth of structure slows, distant galaxies recede beyond visibility, and the expansion of space accelerates inexorably. The behavior of the cosmos is determined not by the presence of mass, but by the persistence of what is essentially nothing. The implications for causality are profound. Objects that seem fixed in the night sky are receding from one another at increasing speeds, not because they move through space, but because space itself is stretching. Observers in the far future will find a universe in which most of what exists today has drifted beyond causal contact. The dominant agent of this evolution is absence, energy embedded in the vacuum, exerting pressure without a medium. Your understanding of interaction, of cause and effect, is challenged when the principal force arises from nothing measurable, yet acts on everything. This balancing act also governs the visibility of history. The cosmic microwave background, the radiation that encodes the early universe, redshifts as space expands. Eventually, Photons are stretched to wavelengths undetectable by any conceivable instrument. Galaxies disappear beyond the horizon. The very records of cosmic evolution are carried away by the expansion driven by empty space. The universe, in this sense, is not only dominated by absence, it is shaped by it. Knowledge, as much as matter, is contingent on this unseen component. The paradox deepens when you consider magnitude. Although the energy density per unit volume is tiny, its constancy across an incomprehensibly vast space produces effects that overwhelm all other contributions. A minuscule energy in a small room is insignificant, yet across billions of light years, it dictates expansion. A universe dominated by presence would behave entirely differently. Structures would grow under gravity. Light would traverse cosmic distances with predictable redshift, and horizons would be determined by the speed of light alone. Instead, absence, the uniform energy of empty space, becomes the architect of the cosmos. In practical terms, matter is ephemeral in its influence. Stars live and die. Galaxies merge, clusters collapse, yet none of these processes alter the expansion meaningfully on cosmological scales. The vacuum energy continues to act uniformly. It stretches space, separates objects, and imposes an inevitable isolation on distant regions. Everything that seems significant locally is transient compared to the inexorable, universal action of what is not. This dominance of absence redefines the meaning of existence itself. The universe's ultimate fate is controlled not by what is present, but by the properties of emptiness. Space itself contains energy, drives motion, and dictates connectivity. Matter and radiation, while visually impressive, are subordinate. The large-scale architecture of the cosmos, the formation and dissolution of structure, and the causal reach of events are all governed by the uniformity of what is absent. Even the human perception of the universe is shaped by this balance. You interpret the cosmos through light, matter, and structure, yet the dominant influence is invisible. The universe's destiny is guided by the silent, pervasive presence of vacuum energy. Observation, modeling, and theory all confirm its effect. Everything you measure today is transient. Everything that seems central will eventually be overshadowed by absence. In this sense, the universe is not balanced on matter, not balanced on radiation, but balanced on nothing at all. A nothing that defines the limits, the structure, and the ultimate fate of everything. Einstein's error reconsidered. The original mistake may not have been adding the term, but expecting the universe to be static. Or it may have been assuming the term had any physical interpretation at all. The equations do not indicate which assumption failed. They only show that one of them must have. Einstein introduced the term to preserve what seemed intuitively necessary, a cosmos that did not expand or contract. This was not a conclusion drawn from observation, but from a sense of conceptual propriety. At the time, astronomical data suggested little about the large-scale dynamics of the universe. Stars and nebulae appeared fixed on the celestial sphere. The idea of a universe in motion on a cosmic scale contradicted common sense. The term was therefore inserted to enforce stillness, a mathematical correction to a theory whose solutions implied otherwise. Once Hubble discovered expansion, the rationale for the term seemed obsolete. The universe was not static, it was stretching. The introduction of the term had been, in retrospect, unnecessary for matching reality. Yet decades later, the same term resurfaced, compelled by observation of accelerated expansion. What was once considered a mathematical convenience, even a mistake, had become an indispensable feature of the cosmos. The term was not wrong in application, but its conceptual framing had been misinterpreted. This raises the question of what constitutes error in theoretical physics. Was it a misjudgment to add the term, or a misjudgment to assume that its addition carried physical meaning beyond mathematical necessity? The equations themselves offer no guidance. They are neutral. They allow expansion, contraction, and a constant energy of space. They do not indicate whether the universe should be static, nor do they explain why a constant exists or what it represents physically. All they provide are relationships between matter, energy, and the geometry of space-time. The ambiguity persists because the term acts differently from every other component in the equations. Matter and radiation have clear, measurable effects, and their behavior aligns with physical intuition. The cosmological constant, by contrast, does not clump, does not interact, and has no particle or field that mediates its influence. It is essential to reproduce observed expansion, yet its existence is unexplained. Any assignment of physical meaning to it is provisional, imposed from human reasoning, rather than dictated by the mathematics. In this sense, Einstein's error may have been philosophical rather than mathematical. He attempted to impose a principle of stillness on a system that does not recognize such a requirement. The failure was not in the equations themselves, but in the expectation that the universe must conform to human notions of stability and permanence. The mathematics never required a static universe. It only required that solutions be consistent with the laws of general relativity. Observation later showed which solutions actually corresponded to reality. The reconsideration of the error also emphasizes the flexibility of physical laws. The same equations that permitted expansion and acceleration could be interpreted in multiple ways depending on assumptions about the universe. The term itself is neutral. It can suppress expansion, drive it, or simply represent a constant energy of space. What is labeled a mistake is in part an artifact of human expectation. The universe does not err, only our interpretations do. Ultimately, Einstein's mistake may be a lesson in humility. The equations faithfully describe relationships between energy, matter, and geometry. They do not prescribe expectation, intuition, or aesthetic preference. When applied without bias, they predict a universe that expands, accelerates, and is dominated by energy that has no conventional source. The error was in assuming that human reasoning could dictate the cosmos, or that the constant must carry immediate physical interpretation. The universe, through the mathematics, simply follows its own logic. In this sense, reconsidering the error reframes the history of cosmology. The cosmological constant is neither an artificial addition nor a failed attempt at precision. It is an inevitable consequence of the equations themselves, revealed through observation. Einstein's misjudgment was in reading human desire into a universe that requires none. The equations work, the universe accelerates, and the error may have been never understanding that reality does not conform to expectation. The lesson is subtle, unsettling, and unavoidable. The cosmos operates according to mathematics that can be fully correct, even when human interpretation is flawed. The equation that still does not close. You are left with an equation that predicts reality accurately while refusing to explain it. Space expands because its geometry demands it. The demand is measured, confirmed, and unavoidable. Whether the mistake was mathematical, philosophical, or conceptual remains unresolved, embedded quietly in the structure of the universe itself. The equation works with precision. It describes the rate at which galaxies recede, reproduces the patterns of the cosmic microwave background, and models the large-scale web of cosmic structure. Simulations based on its terms align with observation at every scale. Supernova, baryon acoustic oscillations, and cluster distributions all confirm its predictions. Every testable outcome conforms exactly to what the mathematics requires. Yet this predictive power is only one half of understanding. The other half, why the universe behaves this way, remains inaccessible. You confront a paradox: absolute accuracy in measurement and calculation, paired with absolute opacity in explanation. Matter, radiation, and forces follow predictable rules. Their interactions are understood in terms of energy transfer, field mediation, and conservation laws. The cosmological constant, by contrast, operates without source or interaction, exerting influence across space without mediation. Its effects dominate the evolution of the cosmos, yet its origin is unknown, and its inclusion in the equations is necessary, not optional. Prediction succeeds, comprehension stalls. The equation embodies a duality between certainty and mystery. Observation confirms the expansion history of the universe, yet the physical reason behind the driving energy remains elusive. Quantum field theory offers enormous vacuum energies. General relativity allows a cosmological constant, and observation constrains a tiny, precise value. The theories, taken individually, work. Together, they yield a tension too vast to reconcile. You can calculate, simulate, and predict with exquisite accuracy, but understanding why the universe exists in this particular configuration remains beyond reach. This duality manifests in the structure of space-time itself. The energy of empty space shapes cosmic horizons, dictates the causal disconnection of distant regions, and governs the eventual erasure of observable history. Galaxies drift beyond contact, radiation redshifts beyond detectability, and the observable universe contracts in a relative sense even as space expands. Every calculation of future evolution depends on a term whose origin is mysterious. The universe unfolds exactly as the equations dictate, but the reason for the dynamics is silent. The philosophical implications are subtle but unavoidable. You are forced to accept that reality operates according to a principle that cannot be derived from known physics, that one of the universe's dominant influences is fundamentally unexplained. The line between mathematics and physical understanding blurs. Equations predict, but they do not clarify. They describe what happens, but not why. You are left with a framework that is complete in its predictive capacity and incomplete in its explanatory power. This incompleteness also challenges your conception of causality and agency. Forces that govern the evolution of matter and light are mediated and measurable. The cosmological constant is not. It acts on everything simultaneously, everywhere, without a carrier, a signal, or a process that fits conventional understanding. Space itself becomes an active participant, yet its activity is understood only in consequence, not in mechanism. The equation imposes a structure, but leaves the meaning suspended. Even historical judgments cannot resolve the tension. Was Einstein's mistake in adding the term, or in expecting a static universe? Was it a misinterpretation of the mathematics, a philosophical misstep, or a failure to separate intuition from calculation? The equations offer no commentary. They continue to predict reality flawlessly while remaining agnostic about human expectations or interpretations. Observation confirms their accuracy, but the conceptual closure never arrives. In the end, the equation stands as a monument to the universe's independence from human intuition. It predicts the expansion, the acceleration, and the eventual isolation of distant regions. It demands inclusion of a term that is empirically measurable, yet theoretically enigmatic. Mathematical consistency is complete. Explanatory completeness is absent. The universe behaves exactly as described, and yet the origin, meaning, and necessity of the term remain unresolved. The equation works. Reality conforms. Understanding lags. This is the quiet unease embedded in modern cosmology. You possess an exact, predictive framework for the universe, yet the cosmos withholds ultimate comprehension. The equation that governs space, time, and structure closes in calculation, but never in reason. It is complete in function, incomplete in explanation, leaving the universe both knowable and unknowable, precisely measured yet fundamentally mysterious.